We are now briefly going to think about the topic of power and energy. And power is just energy divided by time, but that's going to be the more relevant quantity in circuits rather than thinking about energy itself. So when we think about the power delivered by a battery, we have the current out of the battery, so that would be like this I, and then we have the EMF of the battery, which is, for an ideal battery, just the potential difference across the battery. So that's the battery that is the power that is being delivered by the battery. Our batteries are supplying power to our circuit. Now, other components are going to use power. So for instance, if we have two bulbs here, each bulb is using power. Now we can say, and here I've said absolute value just to not get into the concerns of sign conventions, but whatever power in magnitude is being supplied must be the total power being used, right? We can't just be losing power because of conservation of energy. So we're going to talk soon, next slide, about what actually this power usage might look like. But even if we don't worry about that, if we think about light bulbs, well, we know that the same current is passing through each light bulb. And we know that the brightness depends on the current. So we can argue, kind of just in a hand-wavy way, that we expect these two bulbs to be the same brightness. We could then say that each of these are using half of the power that the battery is supplying. There's no reason to say that one is using more than the other as long as they're identical. And we can talk more about how to actually calculate this in a second, but that's the way to think about this, that the battery is supplying power and the stuff in the circuit is then just using that power. The units of power are watts. Power was introduced in the first half of intro physics and mechanics, but it's not a quantity that we think that much about. And so watts are the overall unit, capital W is common, and then the joule per second is how that breaks down, so energy divided by time. Something that you'll see is when you're thinking about situations where you're getting billed for power, like when I have to pay my utilities bill, my electric bill, that frequently will then say kilowatt hour, and we're actually multiplying power in that case by time, which actually gives us back energy. But instead of just talking about joules, the power company charges you in kilowatt hour. So that's a fairly minor point. So where is this power being used, or how is it being used? Now I'm going to start with with resistors, not light bulbs, but come back to the bulbs at the end. So a resistor is actually taking our electrons and it is colliding them with what is around. And so we are actually taking the kinetic energy of the electrons that are in our drift and converting it into thermal energy. So if you think about this, it's doing an energy transformation. One option is you can say that it's converting the chemical energy that was originally in the battery into thermal energy, but you could then say, well, the chemical energy of the battery became the kinetic energy of the electrons that then became thermal energy in the resistors. And if you remember, when we first met current, we said that one of the indicators of current is that the wire gets warm. In that case, we're not talking about an ideal wire. We're talking about a wire that acts as a resistor. So there's a couple different ways to calculate this that are all equivalent. So here we're talking about the power through a resistor, so R for resistor, and we can use Ohm's law to just express this in different ways. So if you notice, there are three different ways of expressing this, but all we've used is Ohm's law, V equals IR for each of them. Now, one thing that's really important to note is that this needs to be done for each resistor separately. There are some exceptions depending on the question you're being asked, but if I give you a circuit that has a bunch of different resistors in it, and I say how much power is dissipated by, for instance, the 2 ohm resistor, you would care about the potential difference across that resistor, and you would be thinking about the resistance of that resistor and whatever the current through that resistor actually is. So the nice thing about having Ohm's law and having these three different versions is notice that in each one you're missing something. In this first equation, you don't actually have R. In the second equation, you don't have the potential difference. In the third one, you don't have current. So as long as you have two of the properties, either the current through, the resistance of, or the potential difference across, you can actually find the power through your resistor. So again, make sure that you're only doing this for one resistor at a time, except in special cases, and that you're using those values for this. So this isn't the potential difference of the battery, this is the potential difference across the resistor. So now, the important thing I mentioned at the end is that a light bulb is basically the same. So for this class, you can approximate light bulbs as being ohmic. At that point, that means they're the same as resistors. Now you might say, hey, I've seen a light bulb that gives off light. I think light has energy in it, so I bet the power of a light bulb actually is due to the light. Not much. So the filament of an old-fashioned light bulb gets really, really hot. And just like hot coals glow orange and give off light due to their temperature, same with a light bulb. An old-fashioned light bulb, and I just mean not a compact fluorescent, not an LED. Physics used to be much easier to teach, like 5 to 10 years ago. But so a normal filament light bulb, an old-fashioned filament light bulb, all you're doing is making that filament get really hot. That heat then results in it glowing. But the whole point we talked about here for resistors is that we're turning the kinetic energy of the electrons into heat. It just then happens that really hot objects give off light. So that's why we can say that light bulbs are basically the same.